Hi, my name is Fabio Comana, and I want to welcome you to my session at NASM's Optima virtual conference. My topic today is on exercise, stress, hormones, and inflammation. Now, individually, they're all huge topics, something that we could talk about for hours. However, we've only got 60 minutes together. And what I want to do is really give us an opportunity to bring these topics together, right? And connect those dots so that you leave with a better understanding of how they are connected. But more importantly, you leave with not only an understanding, but also applications that you can use with your clients. So let's kind of jump into this. First thing I want to do is kick off with a question. The question I want to ask you to start off with is, number one, do you believe stress is bad for you? Number two, do you think inflammation is harmful? So take those, think about them for a second, and then I want you to table them, and then I want to kind of ask you this third question. Which would you choose? Do you believe that stress is harmful to the body and it needs to be managed, avoided, or even reduced? Or do you think that stress is actually helpful and we should embrace it and utilize it in ways that can help promote a healthy and long life? And so to kind of answer that question, I want to talk to you about a study that was conducted several years ago. All right. And the study looked at a large sample of the population, about 30,000 people, and they tracked them for 8 years. And it really involved two key questions. The first question that was asked was, how much stress have you actually experienced in the past year? Question number two is, do you believe that that stress is harmful to your health? Now, you'd expect the logical answer was the people that said they didn't experience much stress and they didn't believe that the stress is harmful, or whether they did or not, had the lowest risk of mortality, and that in fact is true. But what was interesting is that the people that actually said that they did experience a high amount of stress, but also believed that stress wasn't harmful, actually had about the same survival rates as those that had low levels of stress. The group that had the highest mortality rate, pretty self-explanatory, was the group that said high levels of stress, stress is dangerous. So what does that tell us? It tells us that stress might be, sorry, I'm jumping ahead of myself. Stress might be more of a mindset, or it might not only be a physiological manifestation, but it might be a mindset of how you are interpreting that stress, which then influences the physiological outcome on the body. And so it's raised this question of whether we should actually be fearing stress or whether we should embrace it. So to go back to those two choices, you could probably choose both of them, because both of them theoretically could be correct. And we've seen several other studies over time that have kind of reached that same consensus, that when we fearmonger or we place this perception of stress being harmful in your minds, it can lead to someone's detriment. We've seen it with people that are trying to control eating, when they've implemented fear-mongering techniques to scare people to stop overeating. Their coping mechanism has been to eat. When we've used those tactics, like putting those horrible pictures on the cartons of cigarettes and the packages of cigarettes like they do internationally, hoping that it would drive people away from smoking, they've actually resorted to smoking more. And there was a great study that was done in New York in several hotels where the researcher, Alicia Crum, actually was curious to understand the perception of whether the housemaids working at these hotels believed that they were physically active enough to promote good health. And so what she did is, in some of the hotels, she placed these big, sort of placards and everything around the place telling people your housework that you're doing on a daily basis constitutes enough physical activity that it's meeting the government standards for promoting good health. And in the other hotels, she did the exact opposite. She informed them that what you're doing is not enough. You still need to find time to be active. And during the length of the study, she was tracking their biometric markers. She was looking at their BMI score. She was looking at their stress level. She was looking at their blood pressure, all these health measures. And what they found was the group, the housemaids in the hotels, where they were actually informed that what they were doing was adequate, instilled in them the belief that they were living a healthy life, actually showed improved health markers. All there was just a perception in the mind. So we've come to this understanding that stress, albeit physiological, is also manifested itself through how we perceive it. But before we talk a little bit more about stress, let me take you through a little bit of the history of stress, right? So what we know from stress is that back in 1936, a endocrinologist called Hans Selye started to discover this concept of how people were reacting to what he called this experience that was creating some anxiety in their lives. He wanted to understand more of the physiological manifestation. So in his research studies, he was using rats. And he decided in one particular study to inject rats with 3 different types of injectables. One injectable was a hormone isolated from the ovaries of cows. The second one was just a pure saline solution, just like you find in your blood. And the third one was this combination of extracts from various organs. Now, his perception was the saline solution should do nothing to them because that's exactly what rats have in their bloodstream. He suspected that the isolated hormone from the cow's ovaries would probably be detrimental to the rat's health. He figured that they might suffer from some ill effects. And then he was uncertain about the kidney and the spleen extracts. So he was just kind of a wait and see. So what he did is here he was injecting these rats, and over time he observed their overall well-being, and he discovered something that was very surprising. A lot of the rats became sick and many of them died, and it was equal across all 3 treatments. And it got him scratching his head. He couldn't understand why. Why was the saline solution creating the same mortality rate as the extract from the cow's ovaries? And what he stumbled upon was actually this, that it wasn't what he was injecting the rats with, it was the actual experience. The rats started to make this association. Every time he'd come into the lab and they'd see him start filling up the syringes from the vials, it triggered a lot of anxiety within the rats. So it wasn't the injectable, but the actual injection that became the source of their stress. And that's what was killing them, because all 3 treatment groups were getting that same injection. And so that kind of got him to replicate this study using different compounds, and he found the exact same results. And so what he started to recognize is that basically he came to this description or this definition that stress is really what he called a non-specific stimulus. In other words, it can originate itself from any source. Much like in the rat study, it wasn't the injectable, but actually the syringe itself, the connection they were making between the syringe and pain, right? So any non-specific stimulus that threatens to overcome or actually manages to overcome our ability to preserve homeostasis is what he then defined as a stressor. And the key thing to take away from that is that really in life, a stressor doesn't have to be biological. It doesn't have to be a bacteria or a virus. It doesn't have to be, the stress of not eating or the lack of sleep. It can be anything. It can manifest itself through any channel. Emotions, social, intellectual, all right, financial, whatever it is. Now, while that stressor takes on different shapes and forms, the manifestation within our body is going to be physiological. And what he did in his other studies is he identified that he looked at rats running on treadmills, and he says, well, that's a stress too, because it's overcoming or disrupting homeostasis, but it seemed to have positive benefits. In other words, the rats were getting healthier. So he defined a eustress as a healthy stress and a distress as an unhealthy stress. I apologize, my slides keep moving because I'm using this digital clicker and I've got to keep my phone on and it keeps jumping ahead of me. So bear with me on that one. So here's the stressors. As I said, stresses can take on any forms. So really the reality is this: your body may not really care about what the stress is. It's just basically the perception of that stress in our minds will determine the magnitude of our stress response. And so there's a term that they use out there called stress inoculation. As an example, let's say you walk to your car late at night one day and you heard some voices in the bushes. It would probably scare you. Your heart rate would go up, your blood pressure would go up, you might start sweating, you might get nervous. You're activating your fight or flight response. But now let's say nothing came of it. It was just benign. There was nothing that came of it. And let's say for the next 2 weeks, you had the same experience where You went to your car and there was that same noises. Over time, you wouldn't have that same magnitude of a physiological response. Your heart rate wouldn't go up as high. Neither would your blood pressure or your sweat rate. That's what we call stress inoculation. It's much like what we do when we give you a vaccination. We are giving you a small dose of that stressor, not enough to overwhelm you, but enough that your body can build some antibodies, and then it goes away. And then at some point during the season, if you get infected with that pathogen, call it a virus or bacteria, right? Generally, we talk about a virus. Chances are you might have a better chance of fighting it. You may not be able to prevent yourself from getting sick, but you might shorten how the effect that this stress has on you. So when we look at our stress response, it's kind of unique, but it's not anything that's by a stretch of the imagination by any means. We are built to handle stresses. In fact, if you think about it, the human species has survived because of our ability to adapt and become resilient against stresses. Our environment is always changing around us. And if we don't adapt to that environment, all right, what ends up happening is we become just extinct. Think of the animals. So you either adapt or you perish to a changing environment. That's really what we're doing. A changing environment is stressful because it's a disruption of homeostasis. And so we are constantly faced all day long with this one form or of stress or another. We don't get enough sleep. We have a commute. We have toxins in the air. We have relationship issues. We have financial issues. We have exercise. We have all these different types of things. And they just seem to kind of do what? Drop in on us at different times. But our body was designed to actually handle that. But the problem is, it's not designed to handle them all at once. We were designed biologically to take on a relatively severe stress. We called it a fight or flight. And think of our ancestors, think of how they lived their lives. Their stress, for the most part, was what? An invading party to their village. All right. Sorry, my remote keeps changing on me. And could have been a saber-toothed tiger coming into your cave to steal your offspring. And so it was a fight to the death or a flight for your life. So it was an intense physiological response where you had to do everything you possibly could. But then what followed that stress was a period of recovery to restore homeostasis, or even still, an ability to adapt to that stress so that you could better survive it next time. That's called adaptation. We do that all the time. Why do we constantly keep going to the gym? And we have this concept called progression. That's a workout coupled with recovery that allows us to adapt to build a stronger baseline, a new homeostatic line, so that we can come back and continue to progress, make us more resilient, make us stronger. All right. And so the idea is that we're built for this stress response, and then we need a period of recovery that has to follow. And if we live like that, we can live a very healthy life. But as I'm going to show you as we go through this presentation, our biology hasn't changed, but the way that we're living our life, the way that we are interacting with stress and that opportunity to recover from stress is something we're not getting. And that's becoming our ultimate demise. So really what I'm saying here is the mindset is shifting. Not only is stress a cognitive perception, but it's also this idea that stress in itself probably won't kill you. Of course, in extreme cases, it will, like an electrical shock or something like that. But generally, it's the inability to recover from stress that is becoming our ultimate demise. I'm going to get this remote figured out at some point, probably by the end of the session, so bear with me. So let's talk about how the stress response works. So let's talk about this fight or flight. Now remember, it's not the only stress response we have. Other researchers have discovered that when humans are faced with a stressor, they can actually respond in different ways. So we have these phrases that have been coined. We hear about a tend and befriend and an excite and delight. So we don't just have a fight or flight, because what they've seen more predominantly in females, and they've studied female primates, is when there was a stressor, call it an attacking party, so another tribe of baboons attacking one tribe, what was happening is the male baboons would go and confront the other baboons, but the females, the first thing they would do is tend to the offspring, and then they would aggregate in numbers to be able to create a stronger line of defense for their offspring, the tend and befriend. And the hormone oxytocin is believed to be instrumental in driving that response. Then we hear of these people that have these super feats of strength where, a car has kind of backed up and kind of, the child is caught underneath the car and they come in and this little petite woman actually manages to lift a 4,000-pound car enough to get the child out. How the hell does she do that? This is that exciting delight where it basically stimulates the mind and fires up the mind. And that does what? This concept of mind over matter can actually drive this idea of that if we're willing to do something, we can. So we've seen all these different responses, but we're going to focus on the one that we all know, the fight or flight, because it is a primary physiological response that many of us experience. And so I want you to use this analogy here. So kind of see if you follow me on this one. Imagine you know of a security guard, or you are a security guard, and your job is to patrol the campus to make sure that everything is okay. In other words, we're preserving status quo. And what you're doing periodically is you're just kind of checking different parts there, and you may be calling back into HQ, but all of a sudden you come across a door that's unlocked or a window that's broken. What are you doing? You're on the radio calling back to HQ, let's call it the processing center, and informing them that something is not right. And then someone at HQ, a decision maker, is going to make that decision to say, this is what we're going to do. Maybe I'm going to send more people out there. Maybe we need to do what? Kind of set an alarm. We have to have some sort of response. Well, the body works the same way. We have, throughout our entire body, on the periphery and internally, we have receptors. We call them sensory receptors. Our eyes, our nose, our peripheral receptors under the skin, and then we have a ton of chemoreceptors within the body that are sensing anything like a chemical change. So think of your core temperature changing. That's a thermoreceptor. Think of a elevation in your blood sugar. That will be a chemoreceptor that's going to say, we got to get that blood sugar down. There's a disruption to homeostasis. In other words, we've disrupted the status quo. And so what ends up happening in this case is we are communicating that back to HQ, who's then going to determine the appropriate response. Well, how do we communicate that? Well, these receptors generally work through neural pathways. And that information will get to the processing center somewhere in the central nervous system, call it the brain, call it the brain stem, could even be a reflex, which would go right through the spinal cord. And what we're going to get is a response. And that's going to come through the motor pathway or the efferent nerve system. And that's going to basically do what? Transmit a nerve impulse to say, this is the response we want. Now, the beauty of the nervous system is that it's rapid acting. It is very, very rapid acting. A nerve impulse can travel at a rate of about 400 feet a second. So once the brain has made a decision, that impulse can get out there and we can bring about a response within seconds. Now, there's some downsides of the neural system. Its effects are short-lived because it is not an energy-efficient system. It takes a lot of energy to do what? Generate what we call resting membrane potentials, to do what? Release, resequester, regenerate our neurotransmitters. That all costs energy. So it's not a very efficient system, which means its effects are going to be short-lived. Not only that, it also has more what we call localized effects, where what it's doing is it's basically taking an impulse and it travels along the length of the nerve. So impulse goes from point A to point B, that's it. So what if we need a multi-system response? Because your fight or flight is a multi-system response. Think of the things that happen. Your heart rate goes up, you breathe more deeply, you mobilize fuels, and you're vasodilating and you're sweating. Those are multi-systems. So the neural system is not that effective in being able to do what? Efficiently activate all these systems. It does, but it's not the most efficient system. Because it's going to fatigue and because it has more of a localized effect, it also has an influence on the second communication system. This would be our hormonal system. So really they work like a 1-2 punch. So what ends up happening is once the neural system is activated, it can then influence the production or the release of hormones. Now this is a little longer. It takes minutes to maybe even hours to happen. And the hormonal system, when it's activated and the hormones are put into circulation, what we have here is a very efficient system. We have generalized circulation because we put the hormone into the blood and it can have its effect everywhere. And as long as that hormone is staying in circulation and binding to receptors, the effect takes place. So it doesn't take that much energy. So that's how our body works, kind of like a 1-2 punch. And so that's the kind of response we're looking for. Now, the question is, what is actually happening? Well, to explain this, I'm going to use an analogy. You see that pie chart right there. Think of that pie chart as your budget for the month. And each of those segments of the pie could be an allocation, financial obligation, or an allocation to some sort of responsibility. Call it your mortgage or your rent, your car payment, your utilities, food, whatever you want to call it. And hopefully you're living with a nice balanced budget. Everything is balanced nicely. You're flowing through month after month. That's called homeostasis. But now we get this disruption to homeostasis. Just like what happens in 1 month if you had a car accident. You have a finite amount of money devoted to your car to pay the car payment, the insurance, gas, whatever it is. But now your car's damaged and the claims adjuster says, well, that's $2,000 out of pocket. You have a problem. Where's that money going to come from? You don't have a bigger pie. This is your pie. That is the total amount of dollars you have. So what you're going to have to do is figure out a way to borrow from other regions. In other words, you're going to have to reallocate some of your resources, which means you may have to cut back on your social budget. You may have to trim a little bit here and there, maybe not spend as much on clothing, whatever it is, to be able to foot that $2,000 bill. Well, take that analogy and think about exactly what's happening in the human body anytime we go into a fight or flight response. So let's talk about some events that are going to be activated. They're going to be ramped up because we need them in order to tolerate, or if you want to use the word survive, this fight or flight response. We're going to need to do what? Increase our cardiopulmonary responses. The heart's going to have to pump harder, pump faster. We're going to have to do what? Dilate our breathing airways. We're going to have to increase our respiratory rates and our force of respiration. So all our respiratory muscles are going to have to be activated. We're going to have to take more blood into the exercising muscles. So we're going to have some vasodilation there. We're going to be mobilizing our fuels. We don't know how much we need, but we're just going to mobilize right now. Those are the very obvious ones. But there's some other ones that most of us don't think about that are very interesting. Number one, our blood tends to clot faster under the fight or flight response. Why? Well, think about it. If you were fighting to your death and you got cut, the last thing we want you to do is to bleed out. So your release of epinephrine, one of the quintessential stress hormones or exercising hormones, actually makes your platelets stickier so they will clot a little faster. Now, that might be okay for an hour workout. But think about if you were in a stress situation 24/7. Think about the consequences of having blood that might clot a little easier if it stays that way 24/7. Think of the consequences of a stroke, an embolism, or a thrombus, right? What else do we have? Well, you've experienced this one before. You've seen it with a dog that's scared. What does a dog do when it's scared? It pees. What do you maybe need to do right before a big event? You might want to say, I need to go to the bathroom. So we increase bladder contractility and we increase large intestinal contractility. Why? Well, if you're going to run for your life, having that extra pound of fluid or extra pound of fecal matter is just going to slow you down. So vacate it. Now, we're just a little bit more civilized. We don't need to do that right before we stand in front of the treadmill. We don't poop our pants, but you get the idea. So sometimes people want to go to the bathroom right before they work out because there might be a little bit of stress associated with the workout, that anticipation of the workout. We see your immune system elevates. You might think, why? Well, remember, don't look at stress as just exercise. Stress could be a pathogen invading your body, virus, bacteria. But we also know that the immune system, again, is very energy inefficient, just like your nervous system. And we've always talked about this concept called overtraining. What do we mean by overtraining? Essentially, we're saying exactly what the theme we're talking about today is that you are going through this period of stress, but you're not allowing enough recovery for the immune system to fully restore itself before you go into the next stressful event. And that repetitive training bout is not allowing enough recovery, and you start to do what? Compromise your immune function. And that's why we see people that overtrain are more prone to injury and illness. And of course, we see increased sweat rates. That's a no-brainer. Well, if those events had to be activated, what it's telling us is that some events had to be inhibited. We had to borrow from somewhere else. So what do you think is not essential during a fight or flight response? Well, it's pretty obvious. We don't need to eat food, digest food, absorb food. So what do? We shut down from the mouth all the way through the end of the small intestine. We shut everything down. That's why you get dry mouth when you're nervous. We're stopping the production of saliva. What do we also see? Well, what other things do we see? Well, for your survival, we definitely need to do what? Have a little bit of this analgesic effect, because if you're going to fight and get hurt, you got to keep fighting. So we have a little bit of a decreased perception of pain. So the body's able to do what? Diminish the sensations of pain temporarily. But what we really see as a big change is this drop in our reproductive, right? So growth, repair, maintenance of tissue. In fact, they've done studies when they looked at women who are pregnant. And they followed them through their pregnancy. Women who, especially in the third trimester, who experienced the high levels of stress actually ended up with preterm and underweight babies versus women who had very low amounts of stress had babies that had superior brain development. Question is why? How would it affect the kid? Well, as we're going to learn a little bit, the chronic manifestation of stress can actually start to affect your hormones. One particular hormone is human growth hormone. So if she was stressed during her pregnancy, during the last trimester when the baby is supposed to be growing, she might be producing less human growth hormone, which means it's compromising her baby's own development. And that's what they found in the study. So this is interesting that the body goes through these acute changes where we're kind of doing an allocation of resources. But I want you to think, for an hour workout, that might not be a bad thing. That's very tolerable. But what if you live 24/7 with this kind of stress? Think of the chronic manifestations of I'm shutting down the upper part of your digestive system. You're not absorbing nutrients very well. So how does that compromise your nutritional reserves? If I'm compromising hormones like human growth hormone, how's that helping you recover and build muscle mass overnight when during your deep stages of sleep, your human growth hormone levels are supposed to be climbing? Think of all these consequences, right? So let's take the stress response and let's look at it particular into the bout of exercise. And I'm going to really look about glucose and fat metabolism during exercise. So I want to spend the next kind of, 15, 20 minutes talking about that. So when we go into a stress response, let's call it exercise, we see some specific hormones that get released, right? I'm showing 4 of them right here: epinephrine, norepinephrine, cortisol, and glucagon. Now, these are all considered to be hormones that get released under a stressful response. So epinephrine and norepinephrine are collectively called our catecholamines, released from the adrenal medulla gland. Sometimes they're called adrenaline and noradrenaline, essentially the same things. Cortisol is released from the adrenal cortex, same region, that little gland that sits on top of the kidneys, but it's from a different region of the adrenal gland. And of course, glucagon is produced in the pancreas. So what do they do? Well, when we talked about a stress response, we need to mobilize fuel. So what are they going to do? Collectively, all of them can take our stored fats and start to break them down. In other words, mobilize them. We like that. They stimulate blood flow. What do we mean by that? If I can vasodilate a vessel, that's going to allow more blood to get in there. So what do epinephrine and norepinephrine do? They can actually, if they bind to the right receptor, a beta receptor, they can create vasodilation. And of course, what they're doing in non-exercising areas is creating vasoconstriction so that we can do what? Preserve blood pressure. Because if I vasodilate everywhere, my blood pressure is going to drop. So while I vasodilate in the exercising muscles, I vasoconstrict in the non-essential entities, organs, and regions. And that's by basically having epinephrine and norepinephrine bind to what we call a beta receptor or an alpha receptor. Beta receptors cause dilation, alpha receptors cause the constriction. Sparing glucose, what do I mean by that? That means I'm holding back to make sure that your body doesn't use glucose. Nope, epinephrine and norepinephrine say, no. We're making glucose available because you need fuel. And can they make glucose? Yes. When we say they make glucose, they're not physically making glucose. They're just making glucose available. How? From releasing glycogen. So we're breaking down stored glycogen, making glucose available. So that's what epinephrine and norepinephrine do. Glucagon is very similar. It does very similar things to those. But we have a problem. If I'm rapidly going through my carbohydrates, what if I run out? So this is where we have one additional hormone, and cortisol. Hate it as if you might. A lot of people think cortisol is the quintessential stress hormone, and they think nothing but negative thoughts about cortisol. Cortisol is very noble here. Cortisol has a very essential job, is to preserve blood sugar, because the glucose that's in your muscle cells cannot be released, which means the only way that you can preserve blood glucose is through your liver glycogen. So the glycogen that's in the liver is broken down and released and put into the blood constantly to preserve your blood sugar. Because if you don't have blood sugar, unfortunately, you're not going to get oxygen to the brain, because your red blood cells can only feed off of glucose. And if they don't have fuel, they can't carry oxygen. And so that becomes a problem. So cortisol is noble in that it is trying to spare glucose. And how's it doing it? Well, one thing we like is it says, how about we shift to burning more fats? We like that, but it also might involve itself in what we call gluconeogenesis, which is the process of making glucose from non-carbohydrate sources, We have several, but the one that we will talk about is from amino acids. And what amino acids? Generally from the amino acids that are already within our body. The big storage depot called muscle tissue represents 99% of the usable protein in our body, right? So that's unfortunately the downside of cortisol. And if you see that illustration in the graph there, what you're seeing is that basically the whole point of all these hormones being released, and they get released at different levels and at different times, and they fluctuate, is to really accomplish one thing: preserve blood sugar. So cortisol is in essence fighting these other hormones, saying, guys, don't gobble up all the glucose out of muscle cells. Don't pull all the glucose out of the blood and put it into the cells to use it for fuel. We got to preserve blood sugar. So that's what cortisol is always doing. So cortisol and all these hormones may fluctuate throughout an exercise bout based on many different variables: the intensity of exercise, the duration of exercise, where you fed before the exercise. There's a whole bunch of variables that can influence those hormonal responses. But the end of the day is we're trying to keep glucose levels somewhat constant. And we do a pretty good job with it by balancing out our hormonal releases. We can switch gears and look at fat. Well, we've pretty much got the same hormones here. We've got three that we've already talked about: epinephrine, norepinephrine, and cortisol, but we've also got insulin. And I want to introduce this one because it's important. So first of all, let's talk about the first three. What do they do? Well, there's two enzymes that we have to talk about now. Two enzymes that are very, very important in the regulation of fat metabolism. One is called hormone-sensitive lipase. Think of the word hormone sensitive, which means its activity is influenced by hormones. And the other one is called lipoprotein lipase. What do they do? Well, HSL is involved in taking stored fats and mobilizing them. What does that mean? Breaking them down into fatty acids so that we can then transport them and feed them into the energy pathways. That's a catabolic event. Breaking down stored fuel is a catabolic event, just like breaking down glycogen. Lipoprotein lipase is a little different, is that it is a enzyme that kind of hangs outside attached to the membrane of a cell. Which type of cell? Could be a muscle cell, could be a fat cell. Well, what's it going to be responsible for? Snagging those fats out of the blood and putting them into the cell. So which cell would you like it to be more active at? Well, I think it goes without saying. We'd like it to be more active at the muscle cell, to pull those fatty acids into the muscle cell so we can burn them as a fuel. And what's interesting is the regional activity of LPL changes. It's not always the same. What changes it? Your levels of activity. Movement, physical activity, and exercise. When you're someone who's more active, that enzyme becomes more active at the muscle cell. What does that mean? It's promoting a greater uptake of free fatty acids into the muscle cell to be used as a fuel. Good thing. Or to be stored after exercise to be used for future. But when you're inactive, unfortunately, it becomes more active at the fat cell. And that means it's more likely to promote the uptake of fat into the fat cells to be stored. And that's where we're building up our fat depots in the body, which is unhealthy. But this is where insulin becomes interesting, because insulin is pretty much a hormone that does the exact opposite of those three. So it does the opposite of epinephrine, norepinephrine, and cortisol. While they activate HSL, insulin actually inhibits HSL. Why? Because insulin is an anabolic hormone. It says, I want to promote uptake, not to be used as a fuel, but to promote uptake to be built into storage. So the reality is this: anytime you elevate your levels of insulin, what you're actually doing in your body is impeding its ability to burn fats as a fuel, which means it has to rely more on carbohydrates. So that's why we always talk, one of the many reasons we talk about controlling your insulin levels is because anytime you have a surge of insulin, you are technically impeding the body's ability to metabolize fats. So let's kind of dig a little bit deeper here. Okay, so cortisol has a positive effect on both of those enzymes. Cortisol activates HSL, activates LPL. The catecholamines are interesting in that they activate HSL when they're binding to a beta receptor. Earlier I mentioned a beta receptor and an alpha receptor. So if HSL under the influence of catecholamines is binding to, if catecholamines are binding to a beta receptor, it's going to activate HSL. If it's binding to an alpha receptor, it's actually going to do what? Inhibit the activation of HSL. Well, that's odd, but guess what? We tend to have more beta receptors in our visceral fat, right? So what does that mean? That means we are more likely to access our visceral fat first. That's not the fat that everyone wants to burn. When we are talking about losing weight, when our clients want to lose weight, they want to talk about the fat that we can see. That's called our subcutaneous fat. The visceral fat is definitely the more dangerous fat because it is able to release inflammatory agents that can lead to heart disease. But that visceral fat is deep embodied around our organs. Sometimes you use this nebulous term, belly fat. It's kind of a confusing term because in your belly region, you have both visceral and subcutaneous fat. But what we do know about visceral fat is, number one, males have more of it than females. Females have less visceral fat, more subcutaneous fat. And their subcutaneous fat is obviously, a lot of more of it is in the hips and thighs. So we say they're pear-shaped. Men happen to have a little bit more visceral fat, right? And certainly a young male has a lot less visceral fat than an older male. So when older men develop that stomach, it's not just subcutaneous fat. It could be the visceral fat that you can't really pinch. So you're trying to pinch them thinking, wow, they must be really fat, but you can only manage a small pinch. It's because it's the visceral fat that's getting larger and you can't pinch that with calipers, right? So that's some of the questions that we have around skin fold composition as we start to deal with men that have a large belly. So men have more visceral fat, right? And that's why men have a higher risk for heart disease. Now, this is also regulated at a hormonal level because estrogen helps deposit fats into the hips and thighs, right? Whereas testosterone, if you have large amounts of testosterone, it keeps some of that fat off of the visceral region. But when your testosterone levels drop, it actually increases the amount of visceral fat deposition. That's why an older man who has perhaps half the amount of fat to a young man may start noticing increases in his abdominal fat or his visceral fat. So getting back to what I'm talking about here, the catecholamines, when they are binding to a beta receptor, they're going to have a more of an activating effect on HSL and vice versa when they bind to an alpha receptor. And given that we have more beta receptors in visceral tissue, especially in men, we tend to see more of the initial fat that we're tapping into coming from the visceral region and not from the subcutaneous fat. Insulin is interesting. Insulin has an inhibitory effect on HSL, but it can have a positive stimulating effect on LPL. And the question is where, as I already talked to you about. Is it at the muscle cell or the fat cell? But here's what we know about insulin. Insulin also tends to deposit into the subcutaneous fat first. So let's think about this. What does this all mean? When your client comes to you and says, I'd love to transform my body, they're charging you with the responsibility of doing what? Of helping them transform their body. What you're getting is this challenge because we want to help them physically see that transformation. But the reality is when they're tapping into their fats under a stress response, the first fat that we go after, more so in men than in women, is that visceral fat, which is not really the fat they want to lose because we don't really see that fat. But then it gets further aggravated by the fact that when we're depositing fat, in other words, we have a surplus of calories, where do we deposit first? Into the subcutaneous fat. So I know it's a cruel joke, but that's just the reality of how things work. Okay, talked a little bit about fat metabolism and talked a little bit about, sorry, my remote is playing with me here. Okay, here we go. Talked a little bit about fat metabolism. We talked a little bit about glucose preservation. What about resistance training? Well, we know that if you train in a certain way, in other words, you manipulate certain variables in training, what are they? The volume of training, the load of training, your recoveries, the eccentric, these types of variables. I've listed a few there. So 4 to 6 sets to point of failure, creating or emphasizing the eccentric phase to create that muscle damage by shortening some of the recoveries to create a little bit of hypoxia or metabolic stress, they call it, doing more compound movements rather than isolation movements, and lifting with slightly heavier loads or doing more moderate loads with short recoveries. These all put stress on the body. And what we get in that post-exercise window is quite quickly is we get a little bit of a surge of testosterone and human growth hormone, which is going to now help activate muscle protein synthesis. And it can be further accentuated by lifting heavy and trying to go to point of failure with a good volume of training, like 4 to 6 loads, where you get stress on the body that elevates cortisol. Because the elevation of cortisol during exercise can also help elevate human growth hormone post-exercise. And when you've got human growth hormone being elevated, even though it's by small amounts in the post-exercise window, several hours later, we can actually see an elevation of insulin-like growth factor. And that is another anabolic hormone. So yeah, we're training and we've got to train a certain way. So we've got to apply the correct manipulation of stress through these variables to get the hormonal response. So we can see how stress and hormones are connected, right? Okay, I haven't talked about inflammation, so let me bring inflammation into this picture. So when we're talking about inflammation, right, now we've got to talk about our immune system. Because I mentioned earlier too, when we're in that acute bout of stress, our immune response elevates. But I also mentioned to you that our immune system is not energy efficient. It demands a lot and it fatigues itself out. And so if you're not allowing adequate recovery over time, this might become problematic for you. And so when we look at our immune system, we really have to look at two different systems within our immune response. We have what's called our innate system. That's what you're born with. It is your primary line of defense. It's rapid acting. So when you get some sort of pathogen into the body, or you get some sort of cut or whatever it causes, we activate through our innate system our immediate or our acute inflammatory response. And that can be activated within minutes. It doesn't take long, right? Minutes to hours, it can go to work. And this is going to take care of infection, damage, whatever you want to call it. Now, we also have what's called an adaptive system. This is where you take your vaccination. So every fall, you might decide to get a vaccination. And what are we doing? We're giving you a small dose of what we suspect will be the virology of that season. And we're giving you a small enough dose that your body says, okay, this is not going to overwhelm me, but it's going to allow me to do what? Build some antibodies. And they'll go away within a few weeks, but you have that, what we call immunological memory, where if that virus is to come back a second time, your body will remember saying, wait a minute, I remember building these antibodies, and it's going to build them more rapidly. So it's not going to avoid you getting sick, but it's going to help you respond more rapidly to it. It still takes a while. This adaptive system takes days. As sick as you ordinarily would without the vaccine. That's the whole premise around it. The problem with this adaptive system is it doesn't last forever. It's seasonal. That's why we have to get vaccinations on a regular basis. But we're going to talk about the innate system. So how the innate system really works, if I go back to what we talked about earlier, remember my security guard scouting. So just like the security guard was on the radio communicating this response to the individual, our immune system does it in a very similar way, but it does it through a chemical messenger. So when the scouting party, if you want to call it the security guards, we have these things called macrophages that are running around, and they're just kind of observing things, and we discover, something's amiss here. Could be what? We don't recognize this protein. This is a foreign, this is an antigen. This is a pathogen that we don't recognize. Or it's, wow, we've discovered damaged tissue, right? And the tissue is damaged, that there's compounds that are not supposed to be in the blood that are now in the blood. We've discovered that there is a disruption to homeostasis, if you want to call it. What we do is basically we initiate our inflammatory response. How do we do that? Well, we release these inflammatory agents called cytokines. And what they do is they then activate a chain of events, all right? And a lot of it is coming through what we call the HPA axis, the hypothalamus pituitary adrenal axis. Now, that doesn't happen immediately. That's just getting activated as part of our immune response. And why do we care about this HPA axis? Well, we're activating the adrenal gland, and that release of cytokines is creating the opportunity to do what? To release the hormone cortisol. Why do we care? Because cortisol actually is able to do what? Turn off that acute inflammatory response. So let's think about it. We think of inflammation as kind of a harmful thing, but actually your body's built in, the innate response to any disruption to homeostasis is what we call acute inflammation, because the release of those cytokines generates the expression of agents that are going to do what? Get to work and rectify that problem. So we see localized swelling, we see the redness. These are all part of the acute inflammatory response. We are healing the body. We are fighting that pathogen. But at some point, we want to turn it off. And that's what cortisol does. Cortisol then does what? Much like the way insulin works, where it binds to a receptor and activates a pathway, cortisol will also bind to, in part of the immune response, bind to receptors that stops the expression of these inflammatory chemicals called cytokines, and then it turns off the acute inflammatory phase. That's a very healthy thing. That's what we want. So cortisol is actually not only noble in its roles in preserving glucose, it's also very important in being able to regulate or modulate our immune response to any stressful event. Now, Some of you may have suffered a series of injuries, and you go to your doctor and your doctor says, we're going to give you a cortisone injection. Or you might have an inflammatory disease where they say, we're going to give you a prescription for a medicine called prednisone. They sound a lot like cortisol. In fact, they are. Call them cousins if you want to. The chemical structure is very similar because they're going to do the same thing. What is prednisone? It's an immunosuppressant. It's doing exactly what we want cortisol to do. We're just doing it through medicine. When you go get a cortisone injection, we're trying to do what? Use it as an anti-inflammatory. That's what cortisol does too. So these are normal responses to the hormone cortisol that we actually want in that acute inflammatory phase. But we also need to know, much like when you look at insulin, once insulin has done its job, we want insulin to go away. So we have to remove it out of circulation. We have kind of a feedback mechanism, right? A negative loop, if you want to call it, to remove it out of the system, to stop doing what it's doing. Well, we've got our immune system activated. We now need to do what? Release cortisol to turn that acute inflammatory phase off. And so in a perfect world, you are doing what? Exposing yourself to a bout of stress. And then what do you have? You have this period of recovery where you can restore homeostasis and maybe even enjoy some adaptation of it, right? And as your body gets to that new level, we can then enjoy another bout of stress and we repeat this process. That's our biological design. That hasn't changed in hundreds of years, thousands of years. What has changed is the way we play the game. We've changed the rules because we've introduced different types of stresses, perhaps stresses that are not purely a physiological thing like doing work, but we've introduced all these psycho-emotional stresses, your commute, your relationship, your finances, your boss. And the downside of it is that they're not doing what? Following that same pathway of a stressful response plus a recovery. We are just piggybacking them all on top of each other. And as you see in that illustration, throughout your day, there's just no periods of recovery. So it goes back to what I said earlier. We're starting to identify that stress in itself might not be detrimental to the human species. It's the inability to recover from stress that is ultimately becoming our demise. Because what you're seeing in the way that we're living life is our biological stress response is still the same, but we're changing how frequently and the nature of the stresses we're introducing to the body. And they're coming in from different sources. Remember, Hans Selye didn't care. He says, it doesn't matter what the stress is, it's a non-specific stimulus. But the manifestation is physiological, and that's becoming our problem, right? So we can look at this in a different way. As you see on this illustration, if we look at the normal healthy response, here you are. You decide to go exercise. You get an elevation. Well, let me back up a little bit. You get activation of the sympathetic nervous system. What happens? Sympathetic nervous system activates hormones. Hormones now do what? Mobilize fats. Fats get put into circulation. Fats get to the muscle cells because you're active. That fat gets taken up into the muscle cell. The muscle cell uses it for fuel. We're a happy camper. We call that eustress. That's a good natural response. Stress, hormone, fat metabolism. We like that. But we've changed the game. We now introduce a different kind of psycho-emotional stress. Body doesn't know the difference. Still do what? Activate fight or flight. Release those hormones. Epinephrine, cortisol, all those hormones are being released like we just talked about. And what happens? Activate that HSL. Fats get mobilized. The fats get put into circulation. And guess what happens? They get to the muscle cell, if they even get there. And the muscle cell says, I don't need them. Why? I got tons of fat stored. We're not using it. But mobilizing those fats, remember, we mobilize from both organs, maybe more visceral in the men, more balanced in the female, perhaps. We got that fat in circulation. And we're getting to the muscle cells, and the muscle cells are like, we don't need it. Or it's not even getting to the muscle cells. It's going straight to the fat cells. And remember, what tissue is more sensitive to cortisol? Visceral fat. So if you've got more cortisol in circulation, which is a stress hormone, and you've got greater LPL activity in the visceral tissue, the fat cells, you're going to end up getting a lot more deposition of fat into the visceral tissue. And that's called chronic stress. And that's the connection we're making, right, between what? Psycho-emotional stress, mobilization of fats. The fats are not being taken up into the muscle cells. This change in LPL activity at the fat cells in the visceral tissue, and the fact that visceral tissue is more sensitive to cortisol, ends up promoting fat uptake into the fat cell. And that can do what? As we know, visceral fat can release inflammatory agents, and that can promote heart disease. So we see this process. Now, I talked earlier, but doesn't cortisol shut down the immune system? Doesn't it shut down pathways? In acute inflammation, it does. But under chronic inflammation, just like insulin, when you bombard your receptors with too much insulin, the challenge you have is that the receptors start to desensitize themselves to insulin. Well, the same thing, cortisol is binding to these receptors to stop the expression of these inflammatory agents. But if cortisol stays in circulation for too long, i.e. chronic stress, however you want to introduce that into the body, those receptors start to desensitize, which means cortisol is not turning off the inflammatory response, which means you are now shifting from acute inflammation into chronic inflammation. So we see some problems here. This is where cortisol, a good hormone, starts to become a bad hormone. It's not the hormone's fault, it's just that we've changed the game. So as I said earlier, cortisol has noble intentions. It tries to spare glucose so that you don't run out in the blood. It tries to do what? It turns off our acute inflammatory phase. But when cortisol is left in circulation for too long, i.e. chronic stress, that same hormone no longer is our friend. It becomes more of our foe, right? So come on, let's change. Here we go. So here's what we're kind of talking about, just to kind of explain this a little further. If we've got cortisol being elevated under normal conditions, so that normal response, we like it. Exercise bout, elevate cortisol, exercise bout goes away, we recover, cortisol levels are back to normal. Love that. But when we have these abnormal responses, here's what ends up happening. Think of the things that we're trying to achieve with our clients. It's a whole bunch of things. What are we doing? We might be trying to boost their metabolism, maybe lose some fat, increase their fat utilization, control their appetite, build more muscle mass. We're trying to do a whole lot of positive things that are creating that transformation. So through our physiological and through our nutritional interventions, we're trying to create these shifts. Many of those shifts are happening because of hormones that are being triggered or influenced. So what do we see during exercise? Sure, we shut down things temporarily, but what we're enjoying after exercise is improved sensitivity to hormones, which means we don't need as much of it, or increased elevations of certain hormones. So we see what? Oh, we see how post-exercise, we talked about, we could see an elevation in human growth hormone, elevation in testosterone. We could see what? You're starting to build more muscle mass, you're going to elevate thyroid stimulating hormone levels, or you're going to actually, as a result of controlling thyroid stimulating hormone, you're going to see increased levels of T3 and T4. We're going to see what? Even things like increased sensitivity to leptin, which means it's going to help you stop you from eating. All right. We're going to see decreased sensitivity to ghrelin, which actually helps usually stimulate your appetite. So we're going to be controlling your appetite. We're going to do all these things. But now all of a sudden we do what? If you think back earlier to what I talked about, under the acute stress of exercise, we had that allocation of resources, which means what we were doing is we were, by that allocation of resources, we were turning certain things off while we're activating other things. Well, what we're doing is temporarily we were inhibiting certain hormones from doing their job. Because what builds muscle mass? Testosterone. What boosts metabolism? The thyroid hormones. All right. What controls our appetite? Leptin and ghrelin. So we were temporarily shifting these hormones as a result of training or interventions and having recovery. We were getting a net positive outcome of these hormonal responses. But here's the catch. This is where we talk about a domino effect, the hormonal matrix. When cortisol stays elevated for sustained periods of time, it, through various different pathways, starts to have an inhibitory effect on some of those positive hormones, which means we're going to see what? Suppressed human growth hormone. Remember the stressed pregnant woman. We're going to see lowered levels of testosterone and estrogen. We're going to see lower thyroid hormones. We're going to see increased resistance to leptin. We're going to see increased sensitivity to ghrelin. We're going to see a whole bunch of changes. Hell, even cellular aging accelerates when there's sustained presence of cortisol. What are these doing? Well, everything that we're striving to achieve through our training is actually being doing what? Wiped away. We're trying to do what? Increase lean body mass, it's taken away. We're trying to increase total energy expenditure, it's being taken away. We're trying to increase resting metabolic rate, it's being taken away. Trying to increase fat metabolism, it's being inhibited. We're trying to control appetite, we're stimulating ghrelin to eat more. Not only that, another thing that happens is this. Cortisol can have a direct effect on your appetite. It triggers the production of a transmitter called neuropeptide Y in the brain, which regulates your appetite center. So when you have sustained levels of cortisol, you are potentially triggering your desire to eat. Not only that, Lifestyle, when you're stressed, you don't sleep as well. If you're less likely to sleep and you spend more time awake, especially with idle time, you have more inclination to eat. Or eating may be a coping mechanism. And what does eating do? It elevates insulin. What does insulin do? Impedes fat metabolism. So you kind of see that there's kind of a vicious cycle here, that when cortisol is used in short acute bouts, it's a wonderful hormone for metabolism of fats, inflammatory responses, right? So when that stress is applied in short bouts where there is recovery that follows behind that, right? Then we're able to successfully do what? Live a healthy life, because our hormonal matrix is in check. However, when we expose ourselves, allow ourselves to be exposed to the chronic effects of stress, and remember, stress manifests itself in any way. It doesn't have to just be overtraining. Your training program could be beautiful. It's the dog pile of other stresses that have taken you to a point where you're not recovering, and that lack of recovering is probably maintaining that level of stress in your body where your cortisol levels stay elevated. Then you see how everything goes backwards. So what do we need to do? As a coach, as a trainer, as a practitioner, we need to devote equal attention that we've given to exercise and nutrition to now this concept of stress. Sure, try and remove those stresses that we consider to be dangerous, but also embrace the reality that stress can be helpful. So the appropriate application of stress with the appropriate recoveries is actually a good thing that actually helps us survive. But what we have to be aware of is that at some point the stress might be overwhelming. And if we recognize that there's no points of recovery, and maybe it means we've got to cut back a little bit of your exercise until you get control of those other stresses, because I, as a practitioner, can have some influence on the volume and the intensity of exercise you're doing. So maybe we deload or we offload, but I can't control your relationship. I can't control your work environment. So you have to manage those. So we have to get into the whole stress management side of stuff, right? And so now the trainer of tomorrow, or the trainer that's elevated himself or herself from good to great, is that trainer that doesn't just have a kind of myopic approach where they just look at this two-dimensional approach to transformation, where it's just nutrition and activity, so movement and eating. But we're also looking at how these are intertwined with looking at stress, and then how stress is intertwined with hormonal responses and inflammatory responses and environment, so that we get quality of life. I can get my slides to change. Okay, so in closing, I want to thank you all for taking time out of your busy schedules to be here, first of all, for attending NASM Optima, our virtual conference, but number two, for taking the time to listen to my session. My email address is on the slides. You're more than welcome to reach me. The slides are available, and I wish you all the very best. And please try some of these interventions. Try to figure out ways that you can integrate stress management, now that you have a little bit of an understanding of how these are connected, into the lives of your clients. Because at the end of the day, if you can demonstrate value where you're helping them 24/7, it's much more effective, and you're generating a lot more value for yourself than just being able to have your sphere of influence in that 1 hour that they're with you 2 to 3 times a week. All right. With that said, thank you again. Best of luck to you.